আজকে আমরা পড়ব যে টপিকটা, সেটা হচ্ছে ডুয়াল স্পেস। এটা ম্যাথামেটিক্স অনার্স সেমিস্টার 6 এর জন্য 4 ক্রেডিট কোর্স, সিসি 14 পেপারের অন্তর্ভুক্ত। আচ্ছা, ডুয়াল স্পেস লিনিয়ার অ্যালজেব্রার মধ্যে পড়ে। এই সিলেবাসে যেটা আজকে আমরা ডিসকাস করব সেটা আছে ডুয়াল স্পেস, ডুয়াল বেসিস, transpose of a linear transformation and its matrix in the dual basis, and annihilators. আচ্ছা, আমরা সবাই জানি যে যদি আমরা একটা ভেক্টর স্পেস নিই ভি, হচ্ছে ওভার এ ফিল্ড এফ, তাহলে জানি যে এলিমেন্টগুলোকে আমরা বলি ভেক্টর, এগুলোকে বলি হচ্ছে স্কেলার। এবং সাপোজ আমাদের আরেকটা ভেক্টর স্পেস আছে ডাব্লিউ। আচ্ছা, এবং ধরি এটাও ডিফাইন্ড ওভার দ্য সেম ফিল্ড এফ, তাহলে আমরা লিনিয়ার ট্রান্সফরমেশন বা লিনিয়ার ম্যাপিংস এর কথা বলেছিলাম ফ্রম ভেক্টর স্পেস ভি থেকে ভেক্টর স্পেস ডাব্লিউ। A linear mapping T from a vector space V to another vector space W is a mapping which preserves the linearity condition. That is, if I take two vectors alpha beta from V and take two scalars A B from the field, then the image of this linear combination under T will be like this. In such a case, we call T as a linear mapping or linear transformation from the vector space V to the vector space W, provided this mapping is defined only when both the fields are same. Now, this linear mapping, often called homomorphisms from vector space V to W. Suppose this given two vector space V and W over the same field F, let L VW is the collection of all linear mapping. This is collection of all linear mappings from V to W, this set. Obviously, we have this is non-empty. LVW is non-empty because we can always define a mapping T from V to W as any alpha for any alpha to V maps to the null element in W. This is always a linear map, so this mapping is always there. This is called the null mapping or zero mapping. So this T is noted as 0. So this belongs to LVW. And this is non-empty subset of linear mappings from V to W. Now, if you take two mapping T1 and T2, take two mappings T1 and T2 from LVW, then this is again a vector we want to show that this is again a vector subspace, the vector space over the field F. So if you take two scalars CD from F, then what about CT1 plus TT2? Let it be T3, denoted by T3. So for any U belongs to V, T3U, that is CT1 plus TT2 of U is equal to C T1U plus T2U that is equal to C T1U T2U, which belongs to W, as T1U and T2U belongs to W. So T3, that is this linear combination, belongs to LUP. Thus, this is a linear space over F, same field F. Now, given a field F, is also a vector space over itself. So we can define a mapping T from V over F to the vector space F for F. And T is linear. Then this mapping T is called linear functional. Linear functional. So what is a linear functional? Linear functional defined over a vector space V is a linear mapping. A linear mapping from V to the field of the vector space V. This is possible because the field itself a vector space over itself. So it is a vector space over F. V is a vector space over S. So we can define linear mapping from this to this. So this is called linear function. Now, given a vector space V over the field F, the collection of all linear functionals over V, this collection of all linear functionals over V is denoted by L, denoted by L VF. This let us denote by V star. This is called the dual space of V. Now, so you see, in the previous case, we have proved that if I have collection of all linear mappings from a vector space V to another vector space W, this forms a vector space over the same field F. Similarly, if I take the collection of all linear functionals on V, that is all linear mappings from V to the field F, then this is also a vector space. That vector space is called the dual space of V.